All right, everybody. So what we're going to be looking at today is section 2.1 in the book, which is set. So just a couple of notes before we get started here. So let's see. So section 2.1 and 2.2 both deal with sets. Both deal with sets. And those are the only two sections from chapter 2 that we're going to deal with right now. There's another section later on that we're going to come back to probably. Um, but I think this is all we're going to do before the test. Also, I'm going to get a practice test up pretty soon for you guys within, I don't know, within probably by Wednesday next week. Um, yeah, so what will the test cover? It'll cover chapter 1 and then up to section 2.2. And practice test means the real test is coming probably in like week and a half, 2 weeks. 2 weeks maybe? Yeah. Something like that. There'll be an official announcement. But the point is that the exam will cover 1.1 up to 2.2. And I think we skipped one section in there, and like 1.3 we didn't cover, and that's fine. So you won't obviously have any material from that on your exam. So that's not for a while, so don't like panic or anything. Also, keep in mind that the way the test is going to work is the test is going to be, what's it called? Take home. So there's not going to be, you're not going to have a time limit to worry about or anything like that. You're just going to download a PDF from Canvas, do it like you're doing a homework assignment, and submit that. So pretty straightforward for you guys. I don't think it'll be a problem. So yeah, so that's coming up soon. And again, the point is about 2.1 and 2.2 is that that's all we're really covering right now from chapter 2, probably, unless I try to do 2.4. But yeah, so anyway, let's go ahead and get started. Also, this is a much easier topic for you guys than the stuff that we've been doing recently on proofs. And that's actually why the exam is going up to section 2.2, is to get some easier material on there, right? The reason it's not just a chapter 1 test is because I felt like, well, you guys would rather have a couple of easy problems on the end, and that'll make the test a little nicer. So that's why we're doing it the way we're doing it, lumping this in with chapter 1. Okay, let's go ahead and get started. So like I said, this is going to be a much easier topic. Probably nobody's going to even watch this video because they're just going to look at the section, and the section is easy. All right, let's go ahead and get started. So set. Well, what's a set? I guess we need a definition. So a set, according to your book, is an unordered collection of objects. And that sounds a little vague. Unordered collection of objects. What kind of objects? Why are they saying it's unordered? We will get to that. So it says unordered collection of objects. Let me just get rid of that. Called elements, or members of the set. Okay. A set is said to contain its elements. That's just vocabulary, right? So if I say, does set A contain 3, then you're allowed to say it that way, right? So that's all I'm doing here, is telling you how to phrase it when you're writing sentences about sets. So a set is said to contain its element. And here is a little bit of notation. So we write, I'll write it down here. We write this symbol, or write it a little clearer. So it sort of looks like an E, but it's not an E. Looks like that. Um, and we write this to denote that the little a is an element of the set big A. Or you could say big A contains little a, but I didn't. I said it this way. So this is important notation. This is just how you write it. And then what else can I do? Copy. Oops. Undo. Undo. No, not on that. Oh, life is hard, guys. Thing doesn't do what you want it to do. Terrible. All right. Duplicate. All right. So if you take that same thing and you put a line through this, you'll never guess what that means. That means that A does not contain little a. Okay, so that symbol. And so, you can read that different ways. I will usually read it as is an element of. So like that's when I see this symbol, say is an element of. All right. So that's okay. That's what a set is. Okay. Now, what is it? It is an unordered collection of objects. So the unordered part matters. That means that it doesn't matter which order, obviously, that you write things in, you're saying the same thing. So, like, let's just write a couple of examples. So, I guess the one thing to note too is that we usually use uppercase letters and any uppercase letters you want, uppercase letters for names of sets. And typically, they'll kind of go A, B, like that kind of thing to start with, A, B, C. Or another thing you see pretty often is that you'll see S, S for set. And then if you use S for a set, then maybe you'll want T for your next set because you're just writing the letters in order, that kind of thing. Um, but it literally doesn't matter, any kind of letter that you want, and just we usually use uppercase, but you don't have to. Okay, so there's two ways to describe the elements of a set. Two main ways. To describe a set. So the two ways are number one, just what do we call it? The roster method, I guess is what they call it. I don't think I ever heard a name for this until this book, but the roster method, which we will see momentarily, and also what we call set builders notation, which you may know from other math classes. So set builders notation. All right, so let's look at roster method first, and it's very straightforward. So with the roster method for denoting a set, what you're doing is you're literally just listing out all of the elements that are in the set. So you just list every element in the set. For example, here's an example. So I'll tell you in words what the set is, but that's not roster method yet. So let's say I want to write the set containing, let's see, lowercase vowel. How do you spell vowel? Two L's? What do you think? One L. Lowercase vowels in English. I don't know what other languages have, right? So how would we write that? The set containing lowercase vowels in English. So what you would do is you give your set a name. So maybe uppercase V. Another thing they do a lot is the letter that they pick for a set name is related to what's in the set. So like if you have a set of, like when we're going to talk about graphs later on, if you are talking about a graph, there's a vertex set. Well, what do they call the vertex set? They call it V. And then there's an edge set. What do you think they call the edge set? They call it E. So just E for edge and V for vertex. So same thing here. If we're doing vowels, maybe we call the set V because V is what vowel starts with. You know, there's no more complicated than that. So V equals, it's a mathematical object, so it can equal something. And then when you're listing out a set, you use curly braces, these guys. Okay. And then anything you write inside of the curly braces is inside of the set. So if we're doing lowercase vowels, that would be A, E, I, O, U. So that's it. That's my set. Okay. And that's just how you do roster method. You just write it out. So yeah, that's it. Okay. Let's do another example. Let's say this is just straight from the book. Let's see the set. They're going to call it O. O for odd. The set O is odd numbers, odd positive integers less than 10. All right. So how would you write that? Well, they told us to call it O. So O equals curly braces because we're writing a set. And then we want odd positive integers. Well, that's easy enough. You just list them. So positive integers. So starting at 1 and all of the odd numbers less than 10. So 1, 3, 5, 7, 9. There you go. That's the set. Okay. Now, something to be aware of is that you'll notice if you look at what we said up here, we just said selection of objects. We did not say what kind of object we were talking about. And there's no rules, like literally no rules. So any kind of mathematical object. So like that's why we did letters up here and we did numbers down here. Doesn't matter. You want to do letters, do letters. You want to do numbers, do numbers. You want to do something else, do something else. Okay. So you can mix. There's no concept of type here. So so you can mix, let's say like types of objects in a set. So for example, if I say the set S is curly braces because we're opening a set, what's inside of the set? Could be anything. What if I do, let's say I do an A, a B, a 1, an X, a 7, my name, and a dog. Okay, that's perfectly fine, right? Now, what are you going to use that set for? I have no idea, but there's no rule that says I can't write out that set. So I did it. All right. And yeah, that's how you do roster notation. Now, something that you may have done in math before, but now you can do it in sets, is the role of dot 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 ellipses. Okay, So use that is to indicate, missing elements that you're supposed to know what they are. Missing elements where the reader is supposed to understand what is being left out. So what does that mean? So something like this. Let me actually highlight this here so you can find it if you look at the notes later. Okay, so what does that mean? What I mean is this, like, oops, not what I wanted. So something like this. If I say, what do I want? So let's say instead of odd numbers less than 10, I want set S of positive odd integers less than 100. Well, now that's harder to write, right? I don't want to list all of the numbers from 1 to 100. So what you would do is you would say S equals, and then you list off enough that somebody is supposed to be able to see the pattern. So like I would go 1, 3, 5, 7. I think that somebody reading this can realize that I'm listing odd numbers. So once I think that they understand that, I put comma, dot, 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 and then I should tell you where to stop. 99. Okay, and so somebody reading this is supposed to realize that all of the odd numbers are supposed to be where that dot, dot, dot is. Okay, so that's shortcut there. So you'll see that it's pretty simple. Yeah, and that's the roster method, right? So we're just listing out sets by listing everything in the set, even if we have to leave some of them out, by writing dot dot dot. Okay, so let's talk about the other method. Let me highlight this here. Oops. Roster method is what we just did. So let's do set builders notation now. Okay, so set builders notation. What is it? So what set builders notation is you define a set by listing the properties that the elements are supposed to have. Define a set by listing the property or properties that the elements must have. Okay, and there's kind of a way that you do it. So I'll write an example and then I'll point out the parts. So here's an example. Let's say we're going to do a set that let's do even numbers this time actually. So let's write, so let's say we want, let's go E to be the even integers between, let's say, negative 100 and positive 50. Okay, so some even integers, right? So how would we write that? So you do write it a little bit like the roster notation. So you do start out by saying E equals, and we still use the curly braces. So you still use curly braces. Okay. Now what's different is this. So inside of the curly braces, the way you start is the first thing you do is you put like a variable name, and I'm going to do something in a minute that I have not defined yet. So we're talking about integers here, right? And in a second, I'm going to tell you that integers use this symbol. So, that's a little bit confusing for now, but, trust me. So what we've got so far in English says this. So when you see the curly braces, that means the set, right, of then the x here is going to be any x, but the x also needs to be an integer because that's what that means. So there's kind of an implicit for all. So when you see the x, it's for all x. And then the z is integers. So for all x in the integers, there's a vertical line. The vertical line just is read such that and after the vertical line, that's where you put whatever properties they need to satisfy. And you can write them in math symbols or you can write them in words. So I don't need to say that x is an integer because that's already what the z does. So we're already looking at integers. So what do I need? I need to be able to say that they should be even and that they should be in between negative 150. And I wasn't clear whether to include negative 150, but it doesn't matter. We'll do one of them. So how would I say that? Well, you can just say it in words. Just say x is even, and x is supposed to be between negative 100 and 50. So you say negative 100 less than, I'll say or equals x less than or equals 50. Right? And there's nothing special there. All this is just exactly what it said, such that x is even and x, well, what it says, in between 100 and negative 150. Why can't I keep writing that weird? All right. Okay. So again, the way you read it, you go the set, oops, sorry, trying to get a pointer here. The set of all x in the integers such that x is even and x is between negative 100 and positive 50. The end. So you close the set. All right. And that's set builder's notation. So it makes it pretty easy to do that. So there's a lot of ways to write the same set. So like I could have written the same set this way. I could have gone, how about E equals, and I just say x in, what if I say x is a real number? But then here I could say, what kind of real number? I could say x is an even integer and x is less than negative 150 again, right? So I put the integer over here instead of over here. Whatever, it doesn't matter. I'm still saying the same thing because I still got the fact that it's an integer in somewhere. That's fine. Okay. So yeah. And that is set builder's notation. Maybe I will look for a couple of examples, but before we do examples, let me just indicate what these guys are. Oops, not that. Like what these guys are about. Okay, so those are standard set names used in math. Like seriously, they're used all over the place. Okay, so these are standard. Did I go to a new page? Yeah, I'll go to a new page. So these are standard sets of numbers used in math everywhere. So if you take a number theory class, or if you take a real analysis class or anything like that, you'll use these same symbols. So, it doesn't hurt to get used to them. So the first one, and by the way, so I'm going to write it this way. But, sometimes you'll see it this way. Let me rewrite them. Okay, you'll see something like that. And what they're doing there when you see this kind of weird notation, so that's an N for natural numbers. But when you see it in print, it's going to be like a script bold, not script, like a math font bold, serif font. So like, in print, it looks like that. But the way that they write it when you're writing them by hand is, you're not going to scribble out a bold font, right? You don't know how to do a bold font. And so what they do is they double up a line to indicate the bold font, because they use a bold font in print. I wrote a bold fold. I can't talk and write at the same time, but I don't know why that was so funny to me. Bold fold. Okay. Double up a line to indicate a bold font. And all right, what are the natural numbers? So the natural numbers are these guys: 0, 1, 2, 3, ... Keep going up forever. Okay, those are the natural numbers, right? Negative numbers are unnatural. The devil's numbers. Okay, so what are it? Double up a line to indicate a bold font: 0, 1, 2, 3, 4, and so on. And they're called natural numbers. All right, what are the others? Lots of others, so let's get to them. So we already saw one of them. So the one that we already saw was the integers. So see that way? And again, you see it's a Z, but you doubled up the line, right? And, you got, again, a bold font Z is what it is in print, but you write it the way that I wrote it. And what is that? So these are integers. So the way you would write integers is, has to start with a ... Doesn't actually, but then like -2, -1, 0, 1, 2, ... Right? So those are integers. Easy enough. Now, something that you have to do a lot is talk about positive integers. Now, notice this 0 here. The 0 is weird. A lot of times you don't want 0, right? 0 has special properties. So you can't use natural numbers for everything. And so sometimes you really do need only positive numbers. So if you need only positive numbers, then you need a way to say positive integers. So you write the symbol for integers, and then you just put a plus on it, and that means positive integers. And you know what those are: 1, 2, 3, ... Okay, and those are positive integers. Easy enough. Okay, next we have rational numbers. So rational numbers are a Q, and again, you want it to be a bold font, so you add this in, because usually a bold Q kind of is shaded like this, and then there's a little tail somewhere. I don't know where. I don't know how to do it, but one of those guys. Kind of looks like that's in a weird place. But I tried to copy the font of the book. Failed. Put it here. Q. So that's a Q, and it is rational numbers. And rational numbers are fractions, right? Any fraction is a rational number, right? So like 3/5 is a rational number. 225 over 717. That's a rational number. Anything that's a fraction is a rational number. So how do you write it though? Well, how do we define it? Well, the way you define it is you say it's the set of P over Q. We have to use set builders. It's the set of P over Q. Those are fractions. And then what are the rules for P over Q? So the rules for P over Q is that to be a proper fraction here, that not proper in terms of proper improper, but in order to be like a fraction, a real fraction here, the P and the Q should both be integers. So you say P is an integer. Q should also be an integer. And then you're not allowed to divide by 0. So you just say, and Q not equal to 0. So that's all fractions. And that's called, the set of rational numbers, a fraction. Okay. And then the rest of them, we can't really write out good definitions for them, but the ones that get used are real numbers, which I already wrote the symbol for. So like that, again, doubled up line for bold font. That's the set of real numbers. If you need positive reals, you do exactly what you did for positive integers. You just put a plus on it. Positive real numbers. And last one that you see a lot is C, which is the set of complex numbers. And if you want to, of course, I don't know how to do real numbers in a short definition, but if you wanted to, you actually could do complex numbers, because complex numbers are, imaginary numbers. So you could say C is the set of A plus BI, such that A is a real number and B is a real number. So if you know what a real number is, then you know what a complex number is. It just is a real number that might or might not have an I on it. And it's complex. Okay. So, right, these are same. Okay. So, yeah, so what do we got? We got natural numbers, integers, positive integers, rationals, real, positive, real, and complex. Okay. And so something you need to be aware of is I highlighted this 0 in the natural numbers, and that's because your book puts it there, but not every book does. Some books leave 0 out of the natural numbers. Okay. So, just be aware. We have it in naturals, but you might see it another way. All right, so those are some sets that you should be familiar with. You can list intervals pretty easily using this kind of thing. So here's some examples of intervals. Intervals, what do I mean by intervals? I mean like intervals. So like when you say A to B, square bracket, you mean all of the numbers between A and B, all of the real numbers between A and B, right? So how would you write that? You would say that that is the set of all X in the reals such that X is greater than or equal to A and less than or equal to B. Okay. And another comment about this, if it's understood that you're talking about real numbers, then they'll leave it off. So if, it is understood that we're talking about reals, you can leave it off. And that's actually true not just about reals, but any set. If you know what it is, you don't have to write it. So what's that look like? Well, you can guess, right? So all your other intervals can be written this way as well. Like if you want the half open interval, so like parentheses over here, then you could say it's the set of all x such that a less than or equal to x less than b, right? So b is not included if you use parentheses over here. Close brackets. And notice I left the r off. You could do this one, a to b, close bracket on the right. So that's the set of all x such that a less than x less than or equal to b. Right? So where's the equals? If you do a, b, parentheses, parentheses, then neither endpoint is included. So that's a less than x less than b. Okay? So those are intervals. So intervals are just sets. Intervals are just sets of real numbers. Okay? So there you go. What else can we say about these? This is called a closed interval. This is called an open interval. And these two guys are called half open intervals. Typically, they're not open or closed because one side's open, one side is not. Okay. Something else to be aware of is that it's okay for sets to contain other sets. So this is just kind of a fact. Sets can contain sets. So what would that look like? Well, I don't know, something like this maybe. So here's an example. So if I write this set of, and then I list some sets, I can go Z, R, Q. What can we say about that set? Well, how many elements does it have? First of all, we're about to talk about the number of elements. We haven't yet, but you can guess, I think. So this is a set. I didn't write what I said. This is a set containing 3 elements. Doesn't have infinitely many numbers in it. It doesn't have any numbers in it. It only has other sets. So it's a set that contains 3 elements. The 3 elements are sets. And that's fine. Okay. Also, like here's an example. So let's say I say A is the set 1, 2, right? And then I have B is the set 3, 4, right? You can have a set like this, C equals open, and I could say, well, what if I have a set that contains the element 1, the element 2, the set 1, 2, the element 3, the element 4, and the set 3, 4, right? That can be confusing to look at, but if you wanted to figure out how many elements this set had, right, let's just count them. So this is 1, 2, this is one thing, it's a set, 3, 4, 5, 6. So C has 6 elements. 4 of them are numbers. What are the numbers? 1, 2, 3, and 4, right? 1, 2, 3, and 4. Those numbers are elements of C. 1, 2, 3, 4. And the other 2 elements are sets, right? Because we got, what do we got? This is a set, and this is a set. So you can have a set inside of a set, even if not all of the elements inside of the set are set. All right. So you just pay attention to those curly braces that are around things, right? Anything inside of curly braces is a set. So if you have multiple sets of curly braces, then you've got multiple sets that you're talking about. Okay. And we will, again, talk about that a little bit more later, but for now, that's it. Let's have another definition. So what does it mean for sets to be equal? Let's write it out. Definition. We say set A and B are equal. How would you write it? You'll never guess. How about this? A equals B. If, and they say if and only if. So I'll say if and only if. They have exactly the same elements. All right. And you can write that in symbols. You can say A equals B. The definition of that is going to be if and only if. And then a logic definition for all x. So x is going to be elements of sets. For all x, if x is an element of A, well, if and only if x is an element of B, right? So this right here, that thing at the end, this, right? X in A, if and only if x in B. So that means everything in A is in B, everything in B is in A. So they have exactly the same list of elements. All right. And that's just what it means to be the same. So that actually reinforces the idea that the order doesn't matter because so if you have A equals 1, 3, 5, and you have B equals, and you write it this way, 5, 3, 1, those are actually the same sets, right? Or they're equal. So if I'll say that, if A equals that, B equals that, then A equals B because the list of elements is the same. The order is different, but that doesn't matter. I'll say, how do I want to say it? Because exactly the same elements are in A and B. So the order that you write them doesn't matter. All right. So that's what it means for sets to be equal to each other. not that much left. Do we have, where are we? Oh man, there's a lot actually left. All right, let's keep going. So let's kind of speed up because we're going slow. Okay. Do I want to talk about Venn diagrams? Guess I do. I guess I have to. All right. So, no, I won't yet. Let's talk about subsets. Subsets are important. So write a big subsets. Okay. So what are subsets? I mean, I think you can guess, right? So we say A is a subset of B if and only if every element of A is an element of B. All right. And then the symbol for it is this. And it kind of looks like greater than, less than. Kind of ugly. I'll rewrite it. So that symbol, so it's round, looks like a U on its side. A is a subset of B. So, right, you want to think of it as this idea. So you can think of it as A is inside B. Okay, that's not the right way to say it, actually. I don't know why I put quotes around that, but right, B is the big one, and A is a subset. So it's inside of B. Of course, every element of A is an element of B. So in words, I'm going to erase that. I don't like that. Okay, so that's a subset. So if you want to write it in symbols, what it would be is this. So you would say, for all x, if x is in A, that implies x is in B. All right. And the arrow does not go both ways, because if you had this, that would be the sets are equal. We don't want the sets to be equal. We only want, if it's in A, it's in B. So the arrow only goes that direction. Okay. Now, the way you would prove that something is an element of, the way you would prove something is a subset is as follows, right? So to prove A is a subset of B, what you need to do, you must show exactly what that kind of logic statement said. X in A implies X in B, right? To disprove A is a subset of B, what you need to do is find one counterexample. So you must find one X that is in A that is not in B. That's how you would disprove that A is a subset of B. Okay? And how would you write that? So also, where can I write it? Put it here. A is not a subset of B. Never guess how to write it. Like that. Okay? All right. Subsets. Okay. So let's talk a little bit about Venn diagrams, I think. So, and then we'll do some stuff with subset. So Venn diagrams here. Oops. So what Venn diagrams are, that's a VEN, is they are kind of a graphical way to indicate, um, set relationships like subsets and whether they overlap and that kind of thing. So it's a graphical tool for showing sets as, subsets or overlapping or not overlapping other sets. And I'm not really going to go through it a lot. I think that you understand this stuff. So, kind of key facts here is for a Venn diagram, you always have some kind of universe, and the universe is like a rectangle. So there should be a kind of a base set or universe U that the other sets are part of. So like real numbers or something like that. All right. And then you draw it as a rectangle. And then any other sets that you want to talk about, you draw as circles typically. Any other sets are drawn as circles. If I'll write that as a separate thing. If the sets, if one set is contained in the other, if let's see, if A is a subset of B, then the circle you draw for A should be inside of the circle you draw for B. And then also, if sets are not contained within each other, but they have some overlapping elements, if only some elements are common between two sets, you draw the circles overlapping. So what does this look like? So we're not going to do a lot of examples here, I don't think. But so let's say that the universe is, let's just say, natural numbers. Right, which we write that way. So the universe is natural numbers. And then let me have the set A is going to be 1, 2, 3, 4, 5. And then the set B is going to be the set 4, 5, 6, 7, 8. Right? And I think you understand how to do this already, but here's the idea. So the universe is a rectangle. Okay, so the universe is a rectangle. And a lot of times they will, put a little U in the corner to indicate that that's the universe. So that's where all the natural numbers are. And then you have the sets A and B. But you know that there's two elements, 4 and 5, that happen to be in both sets. So what you would do is you would draw A as a circle, and you would draw B as another circle, like that. And, you could label them. You could say, this is A and this is B. Yeah, write that so you can see it better. That's B. And then where are the elements? Well, you can even draw the elements in because you can say, well, A is supposed to have 1, 2, 3, and 4, 5. Well, you could put the 1, the 2, and the 3 there. You have to put the 4 and the 5 in the middle because 4 and 5 are in A and B, and that's everything in A. Now, B has 4, 5, 6, 7, and 8. We already wrote the 4 and the 5, so then 6, 7, and 8 are over here, right? Now, what's outside of the circles? Well, outside of the circles are all of the other natural numbers. So like, zeros out here, 1, 2, 3, 4, 5, 6, 7, 8 are not, but then you got a 9, 10, 11, 12, 13, 14. I don't know why I put a comma. 15, 16, etc. You don't draw those in usually, but all of the natural numbers are there in the universe, but they're not part of A and B, so you don't draw them inside of A and B. All right, and that's a Venn diagram, and that's a Venn diagram. So there you go. Not a lot to say about it. Okay. So let's see. Let's talk about subsets here. Example. Your book likes problems like this. They're not complicated, but they'll say like let A equal 1, 3, 5. B equals 1, 2, 3, 4, 5. C equals let's say 1, 5. Okay, so they'll give you some sets like this, and then the question will be which sets are subsets of other sets. Right, and you have to actually list them all, like all of the possibilities, right? So like A could be a subset of B, B could be a subset of C, B could be a subset of A. Like there's a lot of possibilities, right? So like the possibilities are these for these three. There's going to be 6, I think, possibilities. So like, get a different color actually. So like A could be a subset of B, or A could be a subset of C, or B could be a subset of A, or B could be a subset of C, or C could be a subset of A, C could be a subset of B, right? So those are all the possibilities, but then which ones are true? And remember that when you write subsets like this, the big set is on the right, okay? So when you say A is a subset of B, then the little set is on the left and the big set containing it is on the right. So like looking at these, which of these are true? Well, all of these 1, 3, 5, 1, 3, and 5 are in B, right? All of these are in here. So A is a subset of B. So this is true, right? Now, what about the next one? Let's look at this. Is A a subset of C? Well, 1, 3, 5, are all of those in C? No. So A is not a subset of C. Right? And then we can continue on and just check all the other possibilities. Is B a subset of A? Well, no, right? Because all of these in B are not in A, right? This is supposed to be the bigger set that contains the little set. So no, I'll write it that way actually. Maybe I should have done that here. Oops. Okay, now let's continue on here. B and C. So B is here. This set is a big set. It's not inside of C. So no. Then we got C subset of A. Here's C, 1 and 5. Are those also in A? Yes. So that's true. And then finally, last one, C a subset. Hey, come on, pointer. Where's my pointer? C a subset of B. Well, 1 and 5 are indeed part of B. So C is a subset of B. Okay, so that's how subsets work. I think they should make sense. Yeah, how would I draw this? Let's draw a Venn diagram just because we're drawing them, and then I think that'll be it for Venn diagrams. Draw a Venn diagram for the above sets. All right. So without even writing what the universe is, because it's usually not necessary, let's just draw a universe. Okay, there it is. And what we need are an A, a B, and a C. So let's look here. It's a little bit tricky here. So just looking at this, I see that C 1, 5 is actually inside of A, right? 1, 5 is actually part of 1, 3, 5. And then I also see 1, 3, 5 is inside of B. So if I want to draw these, what I have to draw is I have to draw C, make it a little bigger, is the smallest one. And the elements of C happen to be inside of A. Let me actually redo that. So there's C, and it has, what does it have? 1 and 5, right? So there's C, and it has 1 and 5. And then 1 and 5 are also inside of A. So I have to draw it like this. So it's a little bit different than we had before. So this is A. A is supposed to have 1, 3, 5. So 1 and 5 are already in C. So the only thing we need here is 3. And then you've got the bigger set B, which be like this. And B is supposed to have 1, 2, 3, 4, 5. So 1, 5, and 3 are already here. So we need just 2 and 4. And there you go. So that's what the Venn diagram would look like. Now, what's the universe? Well, I didn't say, but it could have been integers, it could have been real numbers, it could have been anything, right? A lot of times they don't tell you because you're just supposed to be able to say, oh, well, we're clearly just looking at 1, 2, 3, 4, 5. They're from some set of numbers. Doesn't matter what. Okay, so those are subset. We have a little bit left here. Let me look at this. Okay, empty sets. All right. Actually, you know what? Yeah, so we're gonna do one more thing, and then there's some stuff at the end of this section, but it kind of goes on a little longer than I thought it did, and I'm gonna do that as part of my next lecture because we're already 1 hour and 4 minutes into this. So let's just do our last topic for today. Let's do the empty set. All right. So what the empty set is it's a set that contains no elements. No elements. So what do you write it? We write it this way. So you write it like that. Now, a lot of times people will write it kind of so it looks like a 0 just with the slash through it. But you'll see a lot of different kinds of notation if you look at different books. It's usually it is the way that I wrote it there, but sometimes you'll see it with a smaller circle, sometimes with a bigger circle, and so on. Uh, Regardless, it's this set. Okay, so what is it? It is the set. Here it is. Nothing in it, right? So curly braces, I used roster notation. It is the set with nothing inside of it. Okay. Now, a couple properties that you need to know. Right. So, I mean, one thing, it has 0 elements. Of course, that's definition, right? Um, so, but also, um, it might not seem like it, but the empty set is actually a subset of every set. Okay, and that's a key fact. Why is that true? Um, so why? That's what I want to talk about. Why? Why is that true? Because the definition of subset is this. So the definition of subset is A side of B if and only if what was it? For all x, x in A implies x in B, right? So let's just use this definition to see if this is true. Um, to check if, what do we want? We want to use the definition to check if the empty set is a subset of any set we want. I'm just going to do the set 1, 2, 3. Right? So if you apply the definition, it says this. For all x, x in the empty set implies x in 1, 2, 3. Right? For all x, if x is in the empty set, then something, right? In words, it says this. For all x, if x is in the empty set, then x is in 1, 2, 3. Right? And so if you wanted to prove that wrong, you would need a counter example. So to prove this wrong, you would need to find an x that is an element of the empty set that is an element of the empty set, but not an element of 1, 2, 3. Well, why can't I write? It's too late, guys. Too late. All right. So to prove this wrong, you need to find an x. Find an x that is an element of the empty set. Well, how are you going to do that? The empty set doesn't have any element. So you're never going to find an element that's in the empty set, but not in the other set. Okay? So that's impossible, right? Oops. Impossible. The empty set doesn't have any elements. So how could it have an element that's not in B? All right. And so that's why the empty set is actually a subset of every other set. in this case, 1, 2, 3. So the empty set is actually a subset of 1, 2, 3, but the same logic applies to every set. To every set, not just 1, 2, 3. All right. And so that's the empty set. Empty set has no things in it. All right. So we will talk more about the empty set when we talk about power sets, which is in section 2.1, but we haven't done it yet. So just kind of a note here before we leave. We have a couple more definitions in 2.1 before we go on to 2.2. Right. Okay, so that's just a note. So if you look at the notes, you don't think we're done with 2.1. So the next lecture is going to be 2.2, but it's also going to be a little bit of 2.1. And yeah, it's not any harder than what we've done. So, I mean, I hope this was an easy lecture compared to the proofs that you guys have been working on. Well, you haven't been working on, but compared to the proofs that we've gone over. So yeah, I will talk to you guys next time. Homework is up now for this stuff. So yeah, go ahead and get started with it, and talk to you next time.